Hey, welcome back. This is lesson 9.2, where we're going to talk about something called the power series. We're going to specifically talk about the geometric power series, and welcome to calculus. We're going to do some integration and differentiation of power series. So, what are these power series about? Well, a series with variable terms like the one I showed here 1 plus x squared plus x cubed all the way to x to the power n and keep going is called a power series. Okay, so really a whole bunch of terms with powers of x added together. Okay, notice that this one is a special power series. This is a geometric power series. Why do I call it geometric? Think back to lesson 9.1. What do we know about a geometric series? Yeah, it has a common ratio, and the common ratio in this case is x, because I multiply x to get to the next term. Now, if it does converge, what must be true about the variable x? So remember from last day, if the geometric series converges, the r value or the absolute value of it has to be less than 1. Now, another way to write this is that the variable x has to be between 1 and negative 1. And by the way, this is called the interval of convergence. So we know that for values of x between negative 1 and 1, this power series will converge. Sometimes we denote this as IOC. Okay? Now, for these values of x, okay, once again, review from last day. This is all about last day stuff right now. Okay? If this converges, we have a formula that calculates the sum. Yes, it's a over 1 minus r. A in this case is the first term, right? There's a, so 1. And what is r? The common ratio is x. So from the sum formula from the previous page of a geometric series that converges, we know that this power series has the expression 1 over 1 minus x. So this means for values of x, or for these values of x, the function f of x equals to 1 over 1 minus x can also be written as the sum of all these powers. Okay? So three things here. This is the same as that, which is the same as that. Okay, so these three things that I highlighted here in yellow, they all represent the same thing. They represent this power series, this geometric power series. Okay? So we need to know how to play around with these three forms of the power series. So here are some examples. I said find a power series for each of the following functions. I'd like you to show four terms and then the general term. Also then give this series using sigma notation and tell me the interval of convergence. Okay? So I look at number 1 and I look at the expression here. It looks very similar to what I have here. But what's different? Well, the only thing I can see here is that I can rewrite this as 1 over 1 minus, using that format, and this becomes negative x. Okay? So using this form here, 1 over 1 minus x, I've rewritten it that way. Which means then this is a geometric series with the a value being equal to 1, and now my r value being equal to negative x. So what that means is if I want to write out the terms, that would be this form here that I'm highlighting in red now, or boxing in red. Okay. I would just say now f of x is equivalent to 1 plus, now instead of it being positive x, I know that my ratio here is negative x, so it would be negative x, and then plus, it'd be negative x all squared, and then plus negative x all cubed, and so on and so on. Okay, which is the same thing as 1 minus x plus x squared minus x cubed, and don't forget plus dot dot dot. So those are the first four terms, and I guess I should give you the general term as well. Hopefully you can see this is just what Negative x to the power of n. Yep, plus dot dot. And therefore, if I wanted to change this into a summation using sigma notation, then I would write this as the summation of n equals 0 to infinity, and the expression would be negative x to the power of n. Or sometimes people will like to rewrite this as the sum of n approaches to infinity, n equals 0 to infinity, and I'll separate this as negative 1 to the power n, and then also x to the power n. Okay? Last but not least, the interval of convergence here would be the absolute value of x being, oops, not x, but negative x, right. Make the change, negative x being less than 1, which of course really just means the same thing because the absolute value of a negative is positive. And so our interval of convergence is this. Okay? So once again, showing 4 terms. There we go. And the general term. There we go. Summation or sigma notation. Here we go. Interval of convergence. Right here. So see if you do the same for number 2. Okay? And let's see what you get. Too scared? Want me to do it with you? Okay. If you want to do it yourself, once again, press pause and come back. If you don't, listen to me as I do this with you too. Notice here I have 3, interesting, instead of the a being 1. And then 1 minus the r value, which is not x, but 2x. So really nothing I've changed here. I guess I didn't have to write this down, but I hope you can see that this is a geometric series. Now with the a value being equal to 3, and my common ratio r being equal to 2x. All right? So once again, we'll do the 4 terms first. And so now, instead of using a is 3, sorry, a is 1 and r is x, we're going to replace it with, a is 3, the r value is 2x, so my next term would be 3 times 2x, which would be 6x. The next term after that, times 2x, would be 12x squared. Okay, and then the one after that would be 24x cubed. Okay, and so on and so on and so forth. Okay. Now, I also could have just taken this expression over here and then replaced the r with the 2x. That will work as well. Either or, this is what you get. Okay. And then if I want the summation now, n equals to 0 to infinity, and the expression here is 3 times, 2x, and I hope you can see that's raised to the power of n. Okay, and by the way, I could have just written that down here too, 3 bracket 2x to the power n plus blah blah blah. This time for the interval of convergence, hopefully you can see that it's actually the absolute value of 2x now that has to be less than 1. I can break that up into this notation. I need to solve for x, so notice that my interval seems to go from negative 1/2 to positive 1/2. So values of x that are between negative 1/2 and positive 1/2 allow this to converge. Okay, number 3. This time I'll use black. How about that? You might be thinking, this doesn't even look like the forms from above. It doesn't even look like 1 over 1 minus x. Well, it can if you write it like this. 1 over 1 minus, and then how would I get 3x in the end? Can you see how this should just become 1 minus 3x? 1 take away 1 is 0, negative is positive. There you go, you get 3x. So knowing this, what you've said here is this is a geometric series. A equals to 1, and now my ratio is 1 minus 3x. Okay? So now to get the first four terms, a is 1. The next term is 1 minus 3x. The next one after that is 1 minus 3x all squared. And the third one after that, or the fourth one I should say, is 1 minus 3x cubed. And so on and so forth. The general term is 1 minus 3x to the power of n. The equivalent summation notation, sum of n equals to 0 to infinity. And the expression is written by 1 minus 3x to the power of n. And finally, the interval of convergence, the absolute value of 1 minus 3x is less than 1. Rewriting it as 1 minus 3x is between negative 1 and 1. Solving this, we'll subtract 1 on both sides. So negative 2 is less than negative 3x is less than 0. And then dividing by negative 3, which actually gives us positive 2/3 x and then 0. But this time, because we're dividing by a negative, we have to switch the signs. Or a better way of saying this is really 0 is less than or less than x, which is less than 2/3. And this is your interval of convergence. Okay. Now, that is just a general way of doing series. Okay. There is also another way of creating these series, and this is by the idea of substitution. And I kind of did that with actually example number 1. Okay. But let's just use the example number 1 expression. And I'd like you to now create a power series for f of x squared. So as a review for number 1, we had this. We found that f of x equals to 1 over 1 plus x, which, if I write it out as an expansion, is 1 minus x plus x squared minus x cubed, and so on. Remember that? So now if I ask you to figure out f of x squared, what do I actually need to do? Well, you just said to me, replace x with x squared. So wherever you see x, replace it with, you got it, x squared. Which means in our expansion here, wherever you see x, replace it with, that's right, x squared. And of course, that simplifies to 1 minus x squared plus x to the power of 4 minus x to the power of 6, and so on. Okay? So using this idea, can you try number 5? Okay, this time using the power series from example number 2. So in example number 2, we have the power series g of x that equals to 3 plus 6x plus 12x squared plus 24x cubed. And so now I'm going to ask you to make this substitution, make it root x, and yes, wherever you see x, make it root x. This will be 12, root x squared is just x, and then here's 24, and this is x, 3 over 2. Okay, done. How else can we create power series? Yes, we can do it by comparisons. We can do it by substitutions. And we can also do it by differentiation. Interesting. So remember that basic power series we learned? The geometric one? It's here again. Notice if I call this f of x, I can now actually ask you for the derivative of this. Yeah, you're right. I can find the derivative. So use the power series for f of x, and now I'm going to ask you to write down f prime of x, okay? And as I take the derivative of 1, that's of course 0. As I take the derivative of x, that's just 1. And then now I have 2x, and I have 3x squared, and so on and so forth. So yes, you can create derivative power series as well. Okay? Ooh, what about this one, number 7? I guess I can take the derivative, j prime of x. Derivative of 1 is 0. Derivative of x is 1. Interesting. What's this? X squared divided by 2 factorial. The derivative of x squared is 2x. So 2x divided by 2 factorial is just x. And then taking the derivative of x cubed over 3 factorial, that's, well, I'll write this out this time. 3x squared over 3 factorial, that's just 3 times 2 times 1. The 3's cancel out, so this actually becomes what? Plus x squared over 2 factorial. Oh, interesting. 4x cubed is the next one, over 4 factorial, 4, 3, 2, 1. Well, that just simplifies to x cubed over, and the 4's cancel out. 3, 2, 1 is 3 factorial. Won't you look at that? And so on and so on and so on. What do you think is going on? Because what I see is that the original function is this. The derivative is also the same. Which function, when I take its derivative, is itself? And if you said that j of x equals to e of x, since the derivative of that is also the same thing, you are right. So this e to the x can be written as a power series here with powers of x divided by factorial. Crazy stuff. So e to the x function, it can be written as an infinite power series. Wow. Okay. Now, we can also go backwards. If we can differentiate, we can integrate. So looking at example number 1, we had this expression 1 over 1 plus, I changed the variable from x to t this time. Okay. And we have this power series of 1 minus t plus t squared minus t cubed and all that. Okay. This time now, I'm going to ask you to anti-differentiate this from 0 to x. Okay. Now, if I were to do this, looking at the left-hand side, this antiderivative gives me the natural log of the absolute value of 1 plus t. And you're going to have to evaluate this from, 0 to x. Now, if I do the right-hand side, interestingly enough, the antiderivative of 1 is t. The antiderivative of minus t is negative t squared over 2. The antiderivative of t squared is t cubed over 3, and so on. And yes, I'm going to ask you to evaluate this from 0 to x. So if I were to now do this on the left-hand side, I plug in the absolute value of 1 plus x minus the natural log of 1 plus 0, which is just 1. That's good. And if I were to do this, I'd plug in x, so this becomes x minus x squared over 2 plus x cubed over 3 minus x to the power of 4 over 4, and so on. And I would subtract off of that 0, right? Minus 0 plus 0. And what you would find here is now that we have the natural log of the absolute value of 1 plus x, okay, is equal to x minus x squared over 2 plus x cubed over 3 minus x4 over 4, and so on. Now, just a quick note here. I'm going to say note. Remember how this only works as convergent if the interval of convergence is there? So it has to be between -1 and 1, right? This is the interval of convergence. Well, because of that, that really means that this absolute value sign is not required. Because the x value has to be between -1 and 1. If I'm going to add 1 to it, I know this is always going to be positive. Okay? So because of that, I can say 1 plus x will always be positive, and then I can say that the absolute value sign is not needed. Okay? So ultimately, I don't have to worry about the absolute value. I can just use regular brackets. It's fine. Because the interval of convergence here is between -1 and 1. So knowing that now, it says, can you use the result that you got from example 8 to actually write a power series for natural log of x? Not natural log of 1 plus x, but of just x. Well then, if I really wanted to do that, hopefully you can see that the natural log of x is actually equal to what we had above, the natural log of 1 plus, but instead of having just x, I better replace that with, yep, x minus 1. Because now 1 plus x minus 1 is just x, which means that in the power series expansion, wherever I see x, I should replace that with x minus 1. Wherever I see x, I should replace that with x minus 1. Wherever I see x, I should replace that with x minus 1. I don't think you want me to say that any more times, but yeah. And so dot, 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 dot. There is our power series for natural log of x. And for number 10 now, I can actually now ask you to write a series for g of x. In this case, g of x is just x squared times ln of x. Well, x squared is fine, that's the polynomial, no problem, but ln x now is actually this expression that you had from above. So really, if I ask you for g of x now, which is just equal to x squared times ln x, I'm going to take each of those terms that I just did above, I'm going to highlight here, and multiply each of those by, that's right, x squared. So now you'll get x squared times x minus 1. You'll get now here x squared times x minus 1 all squared over 2. And then now you'll get x squared times x minus 1 cubed over 3. And here you get the x squared times x minus 1 to the power 4 over 4. And then see how I can create and build more infinite power series? Yeah, pretty cool. And so all these things like ln x and e to the x, and you'll figure out later on sine x and cosine x, these transcendental functions can actually be written out using infinite power series. Bizarro, but true. All right, crazy stuff today. We'll do more crazy stuff in the next lesson. Okay? So really try to get this down, this whole idea of a power series, and then come back for lesson 9.3, and we'll talk about some more specific types of series called the Taylor and Maclaurin expansion or series. See you then.